purpose of today's video is to continue our discussion on orbital notations and how they represent the electron cloud or quantum mechanical model. In today's video, we're going to be discussing the energy levels, subshells, and orbitals that are represented when we write out an orbital notation. We're also going to be looking at how we can actually represent the orbital notation in a more abbreviated form called an electron configuration, and then finally the shorthand orbital notation and shorthand electron configuration. Now, in order to do this, the first thing that we are going to do is label our periodic table like we did during the last lesson. So we have our S block here, our D block in the middle, our P block over on the right side, and finally our F block on the bottom. And if you remember back to our previous lessons, we begin by numbering our S block starting with number 1. Our P block starting with number 2. Our D block starting with number 3. And our F block starting with number 4, although since we're focusing our attention today on these first 5 rows or periods on the periodic table, we actually won't be getting to the 4F or the 5F, but it does look nicer if we just label the whole thing. So let's start with an example. Let's look at something like silicon. Silicon has an atomic number of 14, which means when we're looking at the neutral atom, the 14 protons from the atomic number have to be balanced with 14 electrons. And those 14 electrons are what we're going to represent in our orbital notation. So, based on our understanding from the last lesson, we remember to put helium over here with hydrogen, and we remember to start with electrons 1 and 2, which are found in the 1s region. So we would write out a 1s. Since it's an S, we draw a single line above it, and we have an arrow pointing up and an arrow pointing down. We then go back to our periodic table and find the next elements. That would be elements 3 and 4, which are here in 2s. Since it's an S, again, we draw a single line above it. There's electron 3, and there's electron 4. Electrons 5, 6, 7, 8, and 9 are over here in this region, so that's the 2p. P's get 3 lines. And remember, when we fill them in kind of weird, which is what some of you guys were struggling with on the last quiz. We have element 5, 6, and 7 are all represented by up electrons. And then electron 8, 9, and 10 are all down-facing electrons. That was based on Hund's rule that said we had to fill in all the ups before the downs. 11 and 12 are over here in the 3s region, 1 up, 1 down. And then 13 and 14, our last 2 electrons, are here in the 3p region. Since it's a P, I'm going to go ahead and fill in all 3 lines, but I only need 2 more electrons to get me my total of 14. So I'm going to stop there. Now, last week we had previewed some other vocabulary terms, and these are things that we're going to continue working with today. So we have energy levels. And we said energy levels were described by the principal quantum number, and it basically just described the distance from the nucleus that the electron was most likely to be found within. They're represented by the numbers, and if we want to figure out how many occupied energy levels we have, we just need to look for the highest number that we drew. So we have some electrons on the first energy level, we have some electrons on the second energy level, and we have some electrons on the third energy level. So our occupied energy levels would be 3. The next thing that we described were occupied subshells. And we said subshells were a more specific region. It's when we not only know the size, or the distance from the nucleus, but also the general shape. And the shapes were represented by the letters. These are the angular momentum quantum numbers. But anytime you have a different number-letter combination, that's a new subshell. So here we have 1, 2, 3, 4, and 5 different subshells. Those are the number-letter combinations. 1, 2, 3, 4, 5. The other vocab term that we talked about briefly last time were the orbitals. And we said orbitals were the most specific description of the region that the electrons were found. Because in order to describe the orbital, we not only had to know the size, the energy level, and the shape, the subshell, but we also had to describe the region based on its orientation around the x, y, and z axes. The individual orbitals are described by the magnetic quantum number, and we can count them by counting these lines that the electrons actually sit on top of. So, for silicon, where we had our 14 electrons, we have a total of 1, 2, 3, 4, 5, 6, 7, 8 orbitals that are occupied. We don't count this last one because there's no electrons above it. And we don't match these two together on a single line because of Hund's rule, where we had to fill the ups in before we could fill in any of the downs. So again, energy levels were 3 because there were 3 different numbers. Subshells were 5 because there were 5 number-letter combinations, and orbitals were 8 because there were 8 lines that had at least 1 electron on top of it. Energy levels, subshells, and orbitals. Now, our goal today is to not only be able to count each of these things, but to maintain that ability and still be able to count them, even if we use a shorter version of our electron cloud model. So, the version that we looked at before was called the orbital notation. And for something like silicon, it always started with 1s, and it always built all the regions that we passed through on the periodic table until we got to the number arrow that represented our element. One thing we can do is go from an orbital notation to something called an electron configuration. And the electron configuration for silicon would look like this. So I have replaced these arrows and the lines, or the orbitals, with a single exponent, a 2, a 2, a 6, a 2, and a 2. And it might be obvious to you that each of those exponents just relates to the number of total arrows that were drawn above the subshell regions. So from this electron configuration, I can still determine the number of energy levels because the numbers, or the principal quantum numbers, are still written. I can look and say I still have a total of 3 different numbers. I can still count the subshells because the number and letter combinations are still written, so I can still see all 5 of those. But it does make it a little bit difficult to count the orbitals. Since the lines aren't drawn, we don't know how many total lines are occupied. Now, for a lot of them, it's just going to be half of whatever the exponent is. So 2, we had 1 line. 2, we had 1 line. 6, we had 3 lines. 2, we had 1 line. The only exception to that is where you have a region that is not completely filled in which case the number of lines is not necessarily half of the number of electrons. Electron configurations are a lot faster to draw, and you're going to have some practice drawing out these electron configurations today. Based on an electron configuration, we can definitely still determine energy level, we can definitely still determine subshells, but orbitals are a little bit more difficult. The other shorthand that we can do is actually, for each of these, we can do what's called a shorthand orbital notation or a shorthand electron configuration. And by putting the word shorthand in front of these, it will actually reduce the amount of writing that you have to do. So the first thing I'm going to do is show you an example of what each of them look like. And then we're going to figure out how to draw them. So for silicon, the shorthand orbital notation would look like this. You see I draw a lot fewer of the arrows. And very similarly, the shorthand electron configuration would look like this, where I don't draw all of the regions. 2 things we need to figure out today. First of all, how do we draw these without having to first draw out the whole thing? And second of all, how can we use these to still figure out the energy levels, subshells, and orbitals, or the principal quantum numbers, angular momentum, and magnetic quantum numbers that we need to be able to describe? So let's look at a new element, and let's figure out how we can write out the shorthand orbital notation and electron configuration, and then we'll do a couple of practice problems together, figuring out energy levels, subshells, and of course the orbitals. So we're going to, for this class, stick with just the first 5 periods or rows on the periodic table. And so we're going to pick an element, and I think we're going to start with one that would be on the far end of what you're going to need to do. We're going to look at tellurium, number 52. In order to write out an orbital notation, we would have to draw out all 52 electrons of tellurium, but 52 arrows takes a while. We're going to focus on the shorthand orbital notation. And in order to figure out a shorthand orbital notation, the first thing you need to do is identify a noble gas. That's an element in group 18. These guys over here the whole way on the right. You're going to have to figure out which of the noble gases comes before the atomic number that you're attempting to draw. So because I'm drawing number 52, I want to know which one of these is closest to 52 without going over. It has to be less than 52. So when I look up here, the noble gas that's above my element is number 36. And to write out a shorthand orbital notation, the first thing you do is write the symbol of a noble gas, something from the far end, in square brackets, and then put its atomic number underneath it. And by doing just that, I have now eliminated having to draw out the first 36 arrows, because this shorthand version allows us to hide all of what we would call the core electrons, the ones that aren't on the lowest floor of the periodic table. And if I am hiding the first 36 electrons, then I'm picking up with element 37. So all I need to do is figure out which of the regions on the periodic table that's in. And that would be our 5s region. S's always get one line. So here's number 37, and here's number 38. And then we look and see where is number 39 at. Well, numbers 39 the whole way to 48 are in the 4D region. Remember, I always fill in all my ups before I fill in my downs. And then we still have number 49, 50, 51, and 52 until we get to our element. They're in the 5p region. P's always get 3 lines. We need 1, 2, 3, 4 arrows. 1, 2, 3, 4 arrows. So this would be my shorthand orbital notation for tellurium. I can very easily turn that into a shorthand electron configuration by simply changing the arrows to exponents. And it would look like that. We're going to do one more example together, and then we'll talk about the energy levels, subshells, and orbitals. The other one that we'll do together is number 28. So let's look at nickel. If I want to represent element 28, I start with the noble gas that's before 28. So that's argon. And I write argon symbol in square brackets with the atomic number of argon underneath it. I then locate the next 2 electrons. So 18, 19, and 20. 19 and 20 are in 4s. S's always get just one line, or orbital, and that's number 19 and 20. And then I have 21, 22, 23, 24, 25, 26, 27, and 28. These are in the 3D. Remember, D subshells always get 5 lines. So this is number 21, 22, 23, 24, 25, 26, 27, and 28. This would be my shorthand orbital notation for element 28, nickel. I can very easily turn that into an electron configuration by replacing the arrows with exponents. 1, 2, 3, 4, 5, 6, 7, 8, which looks like this. So if I'm looking at nickel and I'm looking at tellurium, I still need to be able to determine the number of energy levels, subshells, and orbitals. And that does become a little bit more difficult when we're looking at these shorthand methods. So first, let's talk energy levels. Energy levels really don't change. Energy levels are always the largest principal quantum number that you drew. So my largest number in my first example of nickel here is a 4. So they have 4 energy levels. Whereas tellurium, the largest number that I drew, they were 5s, so this has 5 energy levels. Energy levels will always be the biggest number. You can also think of energy levels as being like the floors on the periodic table, or these periods, these rows. Because tellurium is on the 5th floor, or 5th row, it has 5 energy levels. And because nickel is on the 4th row, that would be 4 energy levels. The next thing that we describe are subshells. And subshells are these individual regions that have both the number and the letter. Now here we drew 2 of them, but we are fairly confident that all 28 electrons do not fit into these 2 regions. There's not enough lines. So we also need to consider the regions that were hidden by the argon. And honestly, the easiest way to do this is just to refer to your periodic table and count these regions. So if I'm looking at nickel, nickel's right here, how many regions do I pass through, including the region that it's currently at? 1, 2, 3, 4, 5, 6, 7. It's in the 7th region, the 7th subshell. So it has 7 subshells. We only drew 2, but the first 5 were hidden in argon. We can do the same thing for tellurium. Tellurium's the whole way down here, and in order to get there, we go through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So tellurium has 11 subshells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You can count the subshells or the number letter combinations based on the picture of our periodic table. The final thing we need to know how to count are the orbitals. And in order to count the orbitals, we really do want to refer to the orbital notations, not the electron configurations, because the orbitals aren't shown very well there. The orbitals are the lines. 1, 2, 3, 4, 5, 6. There are 6 occupied orbitals showing for nickel. But we do know that all 28 electrons aren't on those 6 lines. There's way too many arrows to fit on just 6 lines. And remember, the Pauli exclusion principle tells us we can't have more than one arrow that either faces up or down on any line, so it's not going to work. The other arrows that aren't showing would be hidden inside of argon. And luckily for us, we know that all of those lines were filled in. Aufbau's principle told us we had to fill in these before we could get to those. So really, to figure out the orbitals, all we need to do is take the noble gas divided by 2, because that'll tell us how many lines were required for that many arrows, and then plus any lines you drew. Noble gas divided by 2 plus any lines you drew. The atomic number of the noble gas divided by 2 plus any lines that you drew that have at least one arrow on top. So 18 divided by 2 would be 9, 10, 11, 12, 13, 14, 15. Nickel has 15 occupied orbitals. Tellurium, 36 divided by 2 is 18. 19, 20, 21, 22, 23, 24, 25, 26, 27. Has 27 occupied orbitals. Notice I counted the ones that only had one arrow. However, if I had an example that didn't have any arrows at all, it would not be counted as occupied. In order to be an occupied orbital, it has to have at least one arrow. So hopefully at this point, you see how we can not only draw the full orbital notations and electron configurations, but also these abbreviated versions, the shorthand. And I hope you're also able to see how we can use the periods of the periodic table to determine the energy level, the individual subshell regions, and our rule of noble gas divided by 2 plus any lines you drew to figure out the orbitals. In our next lesson, we'll continue discussing the material or the properties that you can determine based on the periodic tables, and we'll be comparing both periods and groups. But for right now, you really should be focusing on the energy level subshells and orbitals and these shorthand versions.